This is a transistor, this is an LED, this is a solar panel. All these devices have different functionalities and are used for different things, but one thing they all have in common is they use the science of semiconductors. The semiconductor that is used is pure silicon. A semiconductor conducts electrical current better than insulators, but worse than metals. This is because the silicon has 4 valence electrons that can bond with 4 other silicons, forming a tetrahedral crystal. That means all 4 valence electrons would be in a bond, so making those electrons escape would take some amount of energy. In the end, you'd only be left with a few free electrons. Since there are free electrons, it can have electrical current, but it doesn't have enough to make it useful. So, semiconductors and mediocre athletes have a secret weapon: doping. It's the same kind of thing in both cases. It's the act of injecting a foreign substance to improve performance. There are 2 types of doping for a semiconductor. The first type is injecting an atom similar to phosphorus. Phosphorus is about the same size as silicon, so it can replace one of the silicons in the structure. Also, phosphorus has 5 valence electrons, so after it uses 4 of the electrons to bond, there will be a free electron left over. That's called N-type. The other type is P-type. That's when you inject an atom like boron. Boron is about the same size as silicon, and it has 3 valence electrons. So that means one of the 4 bonds it makes with the silicon is incomplete. We say there's a hole there. It's much easier to describe the way the holes move instead of the electrons going into the empty spaces. We then have to say the holes have a positive charge, since it's kind of like the opposite of an electron, which has a negative charge. You might think that makes N-types negative and P-types positive, but that's not true. Both are neutral since they contain just as many protons as they do electrons. The type's name just describes the charge that is free to move. When it comes to making an LED or solar panel, you need an N-type next to a P-type. Well, I shouldn't say next to because it's way more complicated than that, but for our purposes let's just say we can just put them next to each other. Free electrons from the N-type will want to fill the holes in the P-type, and the holes from the P-type want to be filled by the electrons in the N-type. So you see the region with the electron hole pairs, where the 2 types meet? That's called the unbiased depletion layer. The portion of the depletion layer that is in the P-type is negative, since there is a negative charge in a place that's neutral. The portion of the depletion layer in the N-type is positive because of the holes. The reason why all the electrons and holes don't try to pair up is because there is a difference in charge in the depletion layer, which creates an electric field. Electric fields point from positive to negative. Since electrons want to travel in the opposite direction of electric fields, they will be repelled by the P-type. So if electrons can't pass through the semiconductor, how can it conduct electrical current? It's because electrical current creates an electric field of its own. Let me explain. If the semiconductor's built-in electric field repels electrons, since its magnitude is large, then if a current is traveling in the right direction, then some of its electric field will cancel out some of the built-in electric field, thus weakening it to a point where electrons won't be repelled. This smaller depletion layer is called the forward bias depletion layer. To get the current going in the correct direction, you'll have to connect the positive terminal of the power source to the N-type and the negative terminal to the P-type. That's the basis of semiconductors. So now we can talk about how devices use semiconductors. For time purposes, I'm just going to talk about LEDs, but I will say solar panels are pretty much just this process reversed. When you connect the battery to the semiconductor and the electrons flow through the wire into the semiconductor, the electrons could fill some of the holes. When it does, the free electrons stop being free. It will become the atom's electron. We should know that when an electron goes to a lower energy level, it transmits light. So an electron going from being free to being trapped in a bond also must transmit light. To figure out what light will be given off, you first must know how much energy that free electron loses. And then you can divide that by Planck's constant to get the frequency. Then all you have to do is look at the electromagnetic spectrum to figure out what color it will be. Unfortunately, I'm out of time, but I hope you enjoyed. See ya.